This is a continuation of what I was doing in the last video. This video is going to be finding eigenvectors and eigenvalues, and I just wanted to mention that what I'm showing you is just linear algebra review, but I promise that finding eigenvalues and finding eigenvectors, I'll talk about why that's super important when we actually dive into the applications of this. So that'll be the next video, but just in case you've forgotten how to find eigenvalues and eigenvectors, that's what this video is attempting to show. One thing to realize with this problem is that over here we have a matrix, and this value lambda is a scalar. And the idea is if we're given some matrix, and we should be able to figure out an equivalent scalar that's going to make this equation true. So just like last video, we can take this and set that equal to the 0 vector by subtracting this from both sides, and we can also combine like terms where we say this is a minus lambda but since this is a matrix and this is a scalar, we need to multiply that by the identity matrix. This equation right here is going to be used to find the eigenvectors. So the eigenvectors, they're going to be vectors, and we're using X arrow for that. Also, according to Cramer's rule, something else that comes out of this equation is that the determinant of a minus lambda I has to be 0. So we're assuming that this eigenvector can't be 0, or it can't be the 0 vector. So basically when we multiply this, we should be getting this thing's determinant should be equal to 0 in order to get that 0 vector. So this equation will be used to find the eigenvalue. Which we're denoting with the Greek letter lambda. Okay, so these are the two equations. I gave them to you in the opposite order. Our first order of business is to find the eigenvalues, then we'll use those to find the eigenvectors. So I'm going to start off, or I guess the way that I'll show you this is by example. So let's say that your matrix A is equal to 1, 2, 2, 1. Okay. So first thing we're going to do is to find the eigenvalues for this. So we are going to be using the equation, the determinant of A minus lambda I must be equal to 0. And we know what A is. We don't know what lambda is though, so we're just going to multiply that by the identity matrix. Right, lambda times 1001 results in this. And say that this is equal to 0 still. So we end up with something that looks like this. As you get more practice with this, you'll start to see that you can kind of skip these steps. I won't require you to show me this step here. I think skipping right to this is a little bit quicker. But when we take the determinant, we multiply these two things and subtract the product of these two terms. So this tells us that 1 minus lambda times 1 minus lambda minus 2 times 2 must be equal to 0. And if I do some foiling or distributing, then I get this. And this should look familiar, right? It's just what we did in chapter 3. Now we have this equation here, and we can solve for lambda. These lambda values that we get from this are going to be our eigenvalues. So we'll just proceed like we normally do to find lambda. I do want to pause here and introduce some vocabulary. This piece here is called the characteristic polynomial. And sometimes you'll see it written as a function, so little p, and then the input there is lambda, since that's the variable in there. Okay, so let's solve it. I can do this one in my head. If I multiply -3 times -1, or sorry, -3 times +1, and I get this. So that means that my lambda 1 is going to be equal to +3, and my lambda 2 is going to be equal to -1, and these are our eigenvalues. Okay, so once we found our eigenvalues, we can use these to find the eigenvectors. And those are going to have the names, or we're going to denote them x1 and x2 vectors. And so 1 is going to correspond with our eigenvalue number 1, and our 2 is going to correspond with our eigenvalue 2. Okay, so we're going to start with lambda 1 equals 3, our first eigenvalue. And the equation that we're going to use is that I minus lambda I times our eigenvalue is going to be equal to the 0 vector. So really what we're doing here is saying a minus lambda 1 I times our first eigenvalue, or sorry, times our first eigenvector is equal to 0, but I think we can, as long as we're keeping in mind that this is our first eigenvalue and we're working on our first eigenvector, you don't necessarily need to write this out.